Hi, so welcome back to Physics IB. Today we're going to do B1, so thermal energy transfers, and we're going to cover molecular theory, temperature scales, specific heat capacity, specific latent heat, thermal energy transfers, and black body emissions. So quick molecular theory, probably already know it, so I'm gonna go through it really quickly. We have solids, liquids, and gases. Here on the screen, you can see the arrangements of the particles, 3 different phases. Solids have a fixed volume, a lattice arrangement, which is very structured and fixed, and the atoms vibrate around fixed positions, and they have strong intermolecular forces, and given a temperature increase, solids expand less than a liquid or a gas for the same temperature increase. Liquids take the shape of their container. They have a pretty random arrangement and can move around a lot more than solids, but not quite as much as a gas. And their intermolecular forces are intermediate. They're not strong, but they're not weak. Then moving on to gases, they completely fill their container. They have a random arrangement, and the particles have high energy and move around in random directions, colliding often between themselves and with the walls of the container. Density, also a pretty straightforward idea. It's the mass per unit volume, and have the equation for it there. Rho density is equal to mass over volume. You probably know how to use it, so I'm gonna move on. Then we have temperature scales. So temperature is a way of looking at the average kinetic energy of the molecules in a substance. So we have the equation here from the data booklet, which is the kinetic energy average is equal to 3/2 kBT, T in Kelvin, I believe. And we have 2 graphs here of common temperature scales. So we have degrees C and Kelvin. I just thought it was really important because they have the same intervals between degrees or kelvins, but they sometimes try to trick you in exams with the scales, and only Kelvin is directly proportional because that starts at 0, whereas that doesn't. So just bear that in mind. Then thermometers, they are a way of measuring temperature. There are several different types, but for example, liquid and glass thermometers, so ones maybe containing mercury, they need to be calibrated every now and then to make sure that the temperature readings are actually accurate. To do this, they use fixed points on scale. So for degrees C, we can use freezing or melting point of water, which is 0 degrees, or the boiling point of water, which is 100 degrees, and see the accuracy of the thermometer and calibrate it that way. Then moving on to specific heat capacity, it is the energy needed to raise 1 kilogram of a substance by 1 Kelvin or degree C, because they're the same. The equation in the data booklet is Q, so the energy is equal to the mass times the specific heat capacity times by the difference in temperature. And yeah, they will give you the numbers in the question, and it's usually pretty straightforward as well. Then we have the specific latent heat of fusion and the specific latent heat of vaporization. They're slightly different, but it's the energy needed to either melt a substance or vaporize it, boil it. The equation from the data booklet here is Q is mass times the latent heat. And again, they will give you all the information you need in the question. They usually also combine it with specific heat capacity. So, for example, they might give you a graph like this and tell you to work out the energy for different places. So here we can see this is raising the temperature. This would use specific heat capacity while it's a solid. So if we maybe take water, H2O, this would be ice when it's ice phase. Then this is the specific latent heat of fusion. And this would be at 0 degrees C. Then this should be the specific heat capacity of water normally, and it raises the temperature of the water until it boils over here. And then we need the specific latent heat of vaporization, and then here is just when it's a gas, and you need the specific heat capacity of water vapor. But yeah, this diagram is very useful, and you need to know this diagram. So now we're going to move on to energy transfers. We're going to start off with conduction. I've drawn a small diagram here of a heat source. In this case, it's a very well-drawn fire. And here we have, for example, a metal fork or any sort of substance. The idea of conduction is that the particles right next to the heat source, these ones start to vibrate more and more, and the vibration will then knock into the other particles here in the solid, and then gradually the vibrations and the thermal energy will move throughout the solid here until it reaches thermal equilibrium, and then the net energy transfer is 0 because the substance is all the same temperature. Now, the best conductors are, in fact, metals. This is because they have a secret hidden talent, because they have mobile delocalized electrons in the solid, and these will move around, and in addition to all the particles here vibrating, banging into each other to move the heat along, the electrons will also travel along the substance, transferring heat energy too. So they're better conductors. So a way of comparing thermal conductivity of substances is by looking at the thermal conductivity. It's a thing that you also have to be able to work out. There's an equation that I've written here below from the data booklet, and you have to also be able to compare all these different conductivities. So the higher it is, the better a conductor it is. So for example here, copper and diamond are better than water and air, which is understandable because often solids are better conductors than liquids or gases because the particles are much closer together, whereas, for example, in a gas, they are moving around randomly and only collide ever so often. Then we have convection. I've drawn here a kettle because I like my tea. So we have another heat source here, another fire, which warms the particles in the water right at the bottom of the kettle. And because water, when it's warm, has a lower density than when it's cold, it will rise, and the colder water molecules will sink because they have the higher density. And then because these colder particles are closer to the heat source, they will then become warmer and the cycle repeats, and that is convection. Of course, this can only happen in fluids because, as I said, solids don't really move because they have a fixed lattice position. Then thermal radiation is the final one we need to know about. I drew a picture of the sun and the earth here, the sun emitting all this EM radiation and reaching the earth in terms of sunlight, ultraviolet, infrared, and so on. This is an important type of heat transfer because it's the only one that can go through a vacuum, so it doesn't need a medium to go through. For example, convection and conduction, they both need a substance to convey the heat energy. So, yeah. Then we have to look at intensity. Again, I don't think this is in the data booklet, but intensity is the power over the area. I drew the sun here and all the energy that it emits, and it emits energy in sort of a spherical fashion like this, and the intensity is reduced every time it goes out because the power stays the same, but the radius is increased a lot. As you can see here, it's got one little thing, and here it's got 9. So it's an inverse square rule, which we come across very often in IB physics. Then we're going to look very quickly at black bodies. So a quick overview, they are perfect spheres that emit and then absorb all electromagnetic wavelengths. Just to bear in mind, these are ideal objects. They're not real, they don't exist, but stars are often close to these. Then we often associate black bodies to graphs like this, where you can see they emit all wavelengths, but they have a peak here, and each of these has a certain temperature. So moving on to Wien's law, we have the same diagram here for the same black body, just different temperatures here. We can see that the peak wavelength is slightly different for each temperature. So Wien's law states that the maximum, the wavelength here times by the temperature is always equal to a constant, and this results in the pattern you can see here in the diagram, where the intensities as they go further to the right, the wavelengths as they go further to the right, the intensities decrease quite a lot, and you end up with these. Looking at luminosity and the Stefan Boltzmann law. The luminosity is the energy emitted per second, and here is how to calculate it. We have the Stefan Boltzmann constant, which is 5.67 times 10 to the minus 8, times by the area, times by the temperature to the power of 4. Now the area, if we imagine the sun here again, emitting radiation in all directions in a spherical fashion, it will create a ball of light like this, and then we have luminosity in the Stefan Boltzmann law. So luminosity is the energy emitted per second, and here is how to calculate it. We have Then we have luminosity and the Stefan Boltzmann law. Luminosity is the energy emitted per second, and it can be calculated by multiplying the Stefan Boltzmann constant, so 5.67 times 10 to the minus 8, times by the area, times by the temperature to the power 4. So for example, we have the sun here, and to calculate its luminosity, we know the constant, but the area is then the area of a sphere, the surface area of a sphere, which is this, and that's how you do it. Then linking to luminosity, we have apparent brightness. That is the luminosity divided by 4 pi d squared. If we imagine the sun again and it emitting EM radiation in all directions like that, it emits it all in, we can assume to be a perfect sphere of light like this. And the d is just the radius here between the sun and the edge of this sphere of light. And we get the apparent brightness, so how brightly you would be able to see the sun in this position. And in the next video, you'll be able to use this equation to work out the solar constant. And that was it for thermal energy transfers. I hope you liked the video. If you have any questions, feel free to comment and we'll get back to you as soon as we can. Otherwise, I hope you have a great day.